Every single calorimetry problem involves the first and second law of thermodynamics. The first law of thermodynamics states that energy is conserved, that it cannot be created or destroyed, but transferred from one substance to another. The second law of thermodynamics states that heat is always transferred from hot to cold. So anything that is hot will give off that heat. Anything that is cold will absorb that heat until they reach something called thermal equilibrium. Thermal equilibrium states that if I have two objects, heat will be transferred until the two objects reach the same final temperature. So the first type of problem was just one equation. The object either absorbed heat or released heat. In the second type of problems, you will always have at least two objects, minimum, in which one will be at a higher temperature, and so it is your hot, and you have one at a lower temperature will represent cold. So the equation gets modified as Q hot equals to Q cold. That means all the energy that the hot object expels or releases is going to be absorbed by the object that is cold. The simplest of the equation is when the Q hot is mc delta T and the Q cold are mc delta T. Since we learned that hot are exothermic reactions, and exothermic reactions release heat, and so they have a negative symbol. Endothermic reaction absorb heat, so they have a positive symbol. So we need to put a negative in front of the Q hot. And in order to make the math simpler, what we are going to do is we're going to distribute the negative sign in. So in the hot side, when I distribute the negative sign here, my T final minus T initial now becomes T initial minus T final. The code still stays as T final minus T initial. The hot substance will always start at a higher temperature, and the cold substance will always start at a lower temperature. So like any other problem, the first thing you want to do is identify the variables. We know this is a Q hot equals to Q cold because there are two substances. One is the metal here. One is the metal here. And then the other substance is water right here. So I'm going to identify the variables first. So we have 84 grams of the metal. And again, if you don't understand, look at the units will help. So that means the metal has a mass, because it's in grams, of 84.0 grams. Are heated to 99 degrees Celsius. So that's our initial temperature. So T initial is equal to 99 degrees Celsius. In a water bath, then place in a coffee cup calorimeter containing 60 grams of water. So that is my second substance. So my water has a mass of 60 grams at 32 degrees Celsius. So that is my initial temperature of the water. The final temperature in the calorimeter is 42 degrees Celsius. That is going to be the T final for both. Why? The water and the metal are mixed, and they're going to reach thermal equilibrium. So the final temperature has to be the same. What is the constant for the metal? So we're looking for the metal. And since water is between 32 and 42 degrees, we know this is liquid state. So C for water is going to be 4.184 joules per gram degrees Celsius. Since we have two substances, we know that the equation is going to be Q hot equals to Q cold. And if I expand the equation, that's going to be mc delta T for the metal which is my hot, because my initial temperature is at a higher temperature, and my water is my cold because it's at a lower temperature. This is equal to mc delta T of the water. I'm going to expand the equation out. So this is going to be mc T initial minus T final, because that is the hot. And this is the metal. And on the opposite side, it's going to just be mc T final minus T initial. Remember, to distribute the sign for the hot, we flip the T initial and final. So now I'm going to plug in, or if you feel more comfortable, you could solve for the C. It is up to you. I'm going to plug in here. So the mass is 84. My C is what we're looking for. My T initial for the metal is 99 degrees Celsius minus 42 degrees Celsius. This is equal to my mass, which is 60 for the water. The C for the water is 4.184 joules per gram degrees Celsius. My T final is 42 degrees Celsius minus 32 degrees Celsius. Now you're going to simplify the math. You're going to do the parentheses work here first. So that's going to be 10. Multiply 60 times 4.8. 4 times 10 to get the right side, which equals 2,510.4. And then you're going to simplify the left side. So you're going to do the parentheses work first again, which will give you 4,788 times the constant. To get the C by itself, I need to divide both sides by 4,788. And C equals to 0.5243 joules per gram degrees Celsius. Pause the video, try this problem on your own, and then check your answer. First, identify all the variables, then it's a lot easier. So here we have a mystery metal that is heated in a water bath, and we know that the metal has a mass of 55 grams. It is heated to 93 degrees Celsius, so that is my initial temperature, in a hot water bath, and is placed in a calorimeter containing 100 grams of water. So I know this is going to be a Q hot equals Q cold, because we have two substances. One is the mystery metal, and then the other one is water. So we know the mass of the water. The mass of the water is 100 grams. And it has an initial temperature of 25 degrees Celsius. And the metal sits in the water until the temperature levels of 29 degrees. So that's my final temperature for both. Remember, they have to reach thermal equilibrium. We know the water, C, is given as 4.18 joules per gram degrees Celsius. Again, we are looking for C for the metal. So this problem is very similar to the previous problem. So we know it's going to be Q hot equals Q cold, because there's two substances. So Q hot equals to Q cold. So we know this is going to be mc delta T of the metal. This is equal to mc delta T of the water. So I'm going to expand my temperature. So if I expand my temperature, mc, that's going to be T initial, because the metal is hot. and we have to distribute the negative sign minus T final, while the code stays at MC T final minus T initial. If you decide to isolate the variables, then we know I need to divide both sides by M T initial minus T final, but this is going to be M of the metal, and this is the T final of the metal. So if I do that, I'm going to divide by M of the metal, and this is going to be T initial minus T final of the metal. This is going to be metal, metal, metal. So on the left side, the mass cancels out and the change in temperatures cancel out. So the equation, if I rewrite it, is going to be C metal is going to be MC T final minus T initial of the water over the metal mass, T initial minus T final of the metal. So now I'm going to plug in the mass of the water. It's 100 grams. The C is 4.18 joules per gram degrees Celsius. My T final is 29 degrees Celsius minus my initial, which is 25 degrees Celsius. My mass of the metal is 55 grams, and my T initial is going to be 93 degrees Celsius minus my final, which is 29 degrees Celsius. So how do we do the work? We do this parentheses work first, multiply the top. We do this parentheses work first and then multiply the bottom and then divide the two. This equals to 0.475 joules per gram degrees Celsius. So you could set up the math either way if you wanted to isolate the variable first and then plug in and do the math, or you could just leave it and do the math as you go along. Pause the video, try this problem on your own, and then check your answer. Again, this is a Q hot equals Q cold because we have aluminum, and so my aluminum has a C constant or heat constant of 0.90 joules per gram degrees Celsius. There's 30 grams of it, so we know that the mass is 30. Look at the units if you're struggling. And it is heated in a water bath to 98 degrees Celsius. That is our initial temperature, and is added to a calorimeter containing water. So our second substance is water. It has an initial temperature of 25 degrees. The final temperature of the calorimeter is 32, so we know this is at thermal equilibrium. So the final temperature has to be the same for both. What is the mass? So we're looking for the mass of the water. We already know the heat constant of water because this is at the liquid state. So that is going to be 4.18 from the previous problem. And now all I'm going to do is set it up and then plug it in. So Q hot equals to Q cold. My hot is my aluminum. That's going to be MC delta T of the aluminum. This is equal to the MC delta T of the water. So now I'm going to expand. So this is going to be MC T initial minus T final because the aluminum is the hot temperature. This is equal to MC T final minus T initial. For the cold temperature, it stays as is. Now I'm going to plug in. I'm just leaving the equation as is. If you want to solve for M, that is fine. So the mass is 30 grams. C is given as 0.90 joules per gram degrees Celsius. The initial temperature is at 98 degrees Celsius minus the final, which is 32 degrees Celsius. This is equal to the mass which we are looking for. My C is 4.18 joules per gram degrees Celsius. My T final is 32 degrees Celsius minus 25 degrees Celsius as my initial temperature. So I'm going to simplify all the left side. So that means I'm going to multiply this parenthesis here and multiply that to 0.9 and 30. On the right side, I'm going to do this parentheses work and multiply by 4.18 and divide both sides by that. So my mass, if you do your math correctly, should equal to 60.9 grams. Pause the video, try this problem on your own, and then check your answer. So here we have 124 grams of aluminum. So I know aluminum has a mass of 124.0 grams. They gave you a C of 0.09 and it's heated to 99, so that's my initial temperature. In a hot water bath and then placed in a coffee calorimeter containing 65 grams of water. So we have a second substance, which is water, and we know water has a mass of 65 grams. The final temperature in the calorimeter is 43, so that means T final is the same for both. We know the C for the water is 4.18 joules per gram degrees Celsius, but we don't know the initial temperature of water, so that means we're looking for T initial of water. And then my final temperature is still 43 because they reach thermal equilibrium. Since we have two substances, this is also a Q hot equals Q cold. So we have Q hot equals to Q cold. Expanding the equation is MC delta T of the aluminum. This is equal to MC delta T of the water. I'm going to expand the aluminum side. This is going to be MC. Since aluminum is the hot, we have to switch our temperature to distribute the negative sign. So this is T initial minus T final. On the right side for the water, the math is going to be easier if you leave it as MC delta T. And we're going to solve for the delta T. You could already expand it out, but the math is a little bit harder if you do that. So it's easier if you leave it as delta T. At this point, now I'm going to plug in. So the mass is 124.0 grams. My C is 0.90 joules per gram degrees Celsius. T initial is 99 degrees Celsius minus 43 degrees Celsius. This is equal to my mass of my water, which is 65.0 grams, times 4.184 joules grams degrees Celsius, times delta T. So you're going to do the parentheses work first, and then multiply by 0.9 times 124, and on the right side you're going to multiply 65 times 4.18 and divide both sides by that. And when you do that, delta T is equal to 23 degrees Celsius. So delta T is equal to T final minus T initial. You know delta T is 23 degrees Celsius. T final was given as 43 degrees Celsius minus T initial. T initial equals to 66 degrees Celsius. For solving for initial temperature or final temperature, sometimes it's easier to solve for delta T because you have less math to solve for, and then at the end expand delta T out into T final minus T initial. However, you could expand it out in the original formula and still calculate it and just do the math correctly. Pause the video and try this problem on your own and then check your answer. So we have a substance copper with a mass of 125 grams. It has a constant of 0.40 joules per gram degrees Celsius with the initial temperature of 97.0 degrees Celsius. It's placed in a coffee calorimeter containing water. So we know we have a second substance, water. The mass is equal to 42.0 grams. And that water's capacity we know is 4.18 joules per gram degrees Celsius. My T initial is 23 degrees Celsius. We're looking for the final temperature in the calorimeter. And the final temperature is going to be the same because it's going to be at thermal equilibrium. Since there's two substances, it's going to be Q hot equals to Q cold. The hot is your copper and your cold is going to be your water. So in this problem, we have to expand it out. We can't solve for a delta T. You have different delta T's on opposite sides. So this is going to be MC. Copper is the high temperature, so it's T initial minus T final. Water is the low temperature, so that's going to be MC T final minus T. I'm going to sub in. Plugging in, mass is 125 grams times 0.40 joules per gram degrees Celsius. So is 97.0 degrees Celsius minus T final equals to 42 grams times 4.18 joules per gram degrees Celsius times T final minus 23 degrees Celsius. So now you need to do the math. So you have to multiply these two, 125 times 0.4, and you need to distribute it by multiplying by 97, and then you have to distribute it to the T final. And when you do that, you get 4,850 minus 50 T final. You need to repeat the procedure on the right side. So 42 times 4.18, you have to distribute this to the T final, which is 175.56 T final minus 4,037.88. Now you have to put all the T finals to one side and all the rest to the opposite side. I am going to move the T final to the right side to make it positive. So I'm going to add 50 TF to both sides. And when I do that, that cancels out. This equals 225.56 T final. I'm going to move the 4,037.88 to the opposite side, so that cancels out, and we can add 4,037.88. We have to get T final by itself by dividing both sides by 225.56. 225.56. You get 39.4 degrees Celsius. To summarize this video in general, if you have two substances and one is hot and the other one is cold, you are going to do Q hot equals to Q cold. Remember, Q hot always releases energy and it will start at the higher temperature. Q cold will absorb that energy and start at a lower temperature. To account for sign, for the hot substance, you want to switch the T final minus T initial into T initial minus T final. The problems we just did are the simplest of the Q hot equals to Q cold. In general, these can have more than two equations, depending on what temperature it starts at or what temperature it ends at.